Okay, so last time we talked about this sort of recursive nature of the definition of the Macdonald polynomials. So we had E mu, the non-symmetric Macdonald polynomial, was defined like this: t to the minus half length of the element v mu times tau u mu check acting on the element 1. So all this is taking place in the polynomial representation. So at the moment, mu is any element of Zn, and these u's and v's were what you got when you decompose the translation t mu into an element of, a minimal length coset representative of the finite. So you should think of this as an element of w mod w finite, by which I mean minimal length coset representative. And this is the element of w finite. Here w finite is just Sn. Okay, and so the key thing we talked about last time was how to get E SI mu from, so I'll shift notation to gamma instead of mu at the moment. So E SI gamma can be gotten from E gamma as follows. So you can just apply a single tau I. Okay, and this is provided there's an inversion in the ith place if gamma I is bigger than gamma I plus 1. So gamma again is an element of Zn. Okay, so this is the property we talked about last time. Of course, if gamma I is smaller than gamma I plus 1, then you can think of this as, you replace gamma by SI gamma and do the same thing. And then you just conclude the same thing except with gamma and SI gamma inverted. Check acting on E SI gamma. And in particular, this means if you act, so I'm trying to now understand what happens if I act a tau I check on E gamma. So in this latter case, this is like acting tau I check squared on E SI gamma. So this is now like I have to act the square of tau I check. And this, if you recall, was exactly, so the tau i's satisfied the braid relations, but not the square relations. And so here, this tau I square is really what, you get those C functions. So this is C minus alpha I check by t, C plus alpha I check by t. So this was the value of the square. So there are some functions, you think of it as some operators only involving the y's acting on E SI gamma. Okay, so this is sort of the additional factor. And if you recall what this factor was, it was the following, where the C function, so it will sort of come up a few times today. So it's plus minus alpha I check is just, so you can think of it as follows, as a t to the minus half outside, then it's 1 minus t something, which is y plus minus alpha I check, divided by the same thing without the t. So it's 1 minus y plus minus alpha I check. Okay, so this is the operator. And observe the key point is that this operator, because it only involves the y's, this acts as a scalar, on the E gammas, okay, on the e's basically. So if you sort of go back and see what we have just done, so the point is, if you apply tau I check on E gamma, the answer in this case is that it's just going to give you some multiple of E SI gamma. Okay, the multiple being whatever scalar this operator acts by. Okay, and one last case. So we looked at the two cases when gamma I is bigger or gamma I plus 1 is bigger, and if they are both equal. So this is a case 3. In this case, one can show that.
Can I ask a question, Viswanath?
Yes, yes.
So this y is defined more generally for plus minus all weights, right?
Yes, yeah.
So would this C also be defined? Can I just replace that by some mu check or something?
I think the more appropriate thing is to look at, this alpha I check is really, it's sort of the C which corresponds to the simple reflection SI. So more generally, if you have other while group elements, you will take sort of products of such things where in place of just alpha I check, you'll put all those positive roots which are mapped to negatives under W and so on. Is that all right, Arun? Is that sort of the right way to think about it? So there's a sort of the C function is sort of associated to W's rather than to arbitrary elements of.
So if it was length 2, suppose it took 2 positive roots to negatives,
Yes.
how would you define that?
So you take the product of all such terms. So if I had, for example, C corresponding to, so I don't know, should I say S1, S2 in the case of SL3 maybe. So what this will do is, so you will get the product of all the C's, I guess. So C, so this maps alpha 2 to negative. So there's an alpha 2 check. And then times this maps alpha 1 plus alpha 2, right? So you put an alpha 1 plus alpha 2. I hope I've gotten the definition right. So it's the product of, so it's the product of all the C's, yes.
Thank you.
Okay, so so this last equation, I just want to point out, if gamma I is equal to gamma I plus 1, then tau I check will just act by 0. Okay, so these are the 3 equations which sort of tell you what happens when you act tau I check on an E gamma. And the answer is, in all 3 cases, that it always gives you some multiple of EI gamma. Okay, so notice here, tau I check acting on, of E SI gamma. So tau I check acting on E gamma was just E SI gamma in the first case. The second case, tau I check on E gamma was some multiple of E SI gamma. The third case, it's 0, so it's again some multiple. Okay. So what this boils down to is the following fact that if you take the span of all these guys. So let me just say this. So if I fix a lambda in decreasing order, so sort of a dominant element of Zn. So you think of lambda as an element of Zn, so I don't know how to say dominant, so a decreasing order, then you can look at all these E's which correspond to, so look at Cx lambda, which is the span. So here everything is the complex span of all the E gammas where gamma runs over the finite while group conjugates of lambda. So this is gamma runs over Sn lambda, okay, all rearrangements. Now observe this is a basis. These are linearly independent. So, so by the way, I should have said that earlier. So notice we didn't say too much else about the E gammas, but one thing that's clear is that they certainly form a linearly independent set inside Cx, inside Cx. Okay, so why are the E gammas definitely linearly independent? In fact, they are a basis eventually, but E gammas definitely form a linearly independent subset of Cx because they are actually simultaneous eigenfunctions of this set of operators with distinct eigenvalues. So if you recall, how did the y's act on your E gammas? A typical y lambda check acting on E gamma produces sort of a monomial in Q and T, which looks like this. So minus lambda check gamma T to the rho V lambda, maybe I should put the V on this side. So V gamma inverse rho gamma lambda check. I should have written the lambda check on the same side, sorry. So let's erase that. So think of it as a function of lambda check. Okay, so observe if I, so the eigenvalues are, you should think of it really as this function. So, or as we did last time, you can just think of it as a single variable q instead of 2 separate variables. And then this is just q to the, what we call, so we wrote t as q power k and thought of this as a single exponentiation like this. Okay, so in some sense, this is the eigenvalue if you wish. For a given gamma, the eigenvalue is really q raised to the that. I mean, it's that linear functional if you wish on the lambda checks on Zn. So you can think of I mean the eigenvalue, which is what we call the evaluation map last time, is really this this map corresponding to each lambda check. You map it to this number q raised to the whatever. Okay, and if for different gammas, it's clear that this is going to give you a different answer. Okay, because I mean the k is sort of independent. I mean you can just look at the power of q. That will already be enough to distinguish two different gammas. Okay? In other words, there exists, if I have two different gammas, I can find some lambda on which, or some lambda check on which those two gammas have a different answer. Okay, so that lambda check, that y to the lambda check, when you act on the two e gammas, will give you two different eigenvalues. The power of q will already be enough to separate them. Okay, so they are a linearly independent subset, in fact, because they are eigenfunctions for this set of commuting operators with distinct eigenvalues. And so I've defined this set here, Cx lambda, and the equations that I just wrote out, which tell you how tau I check acts on an E gamma. Okay, so what that now tells you is that on this space, see the tau I check action on this basis. So what's now the basis of Cx lambda? I can just take all the E gammas as gamma varies over the conjugates of lambda. So this is, recall, this is a basis now of Cx lambda. Okay, so the tau I action on this is very, very simple to describe in some sense, because what we have just said is that how does tau I act? It takes an E gamma and maps it to some multiple of ESI gamma. Okay, so by this I mean potentially some multiple. Okay, so in that basis, it has this very nice sort of description. Okay, now the question here is, what about the TI action? So that's again something that we want to understand. So recall one of the things that sort of Raghavan mentioned during his lectures, sort of something from Arun's notes, which is that the tau i's are sort of to be thought of as some sort of replacement for the TIs with better properties relative to the y's. Okay, but we sort of want to think also in terms of the t's sometimes. And so here's the here's a relation between the tau's and the t's, which is very useful. So if you sort of recall what the tau was, it was the t plus some additional term, okay, which looks like this: ti plus t to the minus half 1 minus t, that's about it, over 1 minus y to the minus alpha I check. So sorry, I forgot to recall it this time. Alpha I check will always mean epsilon I minus epsilon I minus 1. Okay, and this back in Raghavan's notation was y to the minus alpha I check, therefore will be y to the minus epsilon I. So that's like yi inverse yi plus 1. So that was our notation. Okay, so this is what tau I check is. And so notice it's very close to the C function in some sense, right? So if you recall what the C function had, it had an additional y to the minus alpha I check term there. Okay, so it's almost the C function. And so you can sort of add and subtract out this term there. You can put in a t y to the minus alpha I check, subtract out that. So this is very close to C minus alpha I check. And if you sort of just do the computation, here's what comes out, that TI, sorry, the left-hand side, which is tau I check. So tau I check has TI, and then the simplification gives you this additional term, t to the half, plus the C function. Okay, this is another way. I've just rewritten the definition of tau I check if you wish. And so here's sort of one way of thinking about it, which again, I will just use as a a way of remembering this computation, that tau minus this C function is the same as Ti minus T to the half. Okay, so so this equation I will use a few times today. So tau I check minus C minus alpha I check Yt is the same as Ti minus T to the half. Okay, so okay, now what does this imply? So we just said that the Cx lambdas are invariant under the tau I checks, right? So this is when you, in fact, it has a very simple description. So this is invariant under the action of all the taus. And this equation above tells you that it's also invariant under the action of all the t's. Okay, why? Because, I mean, this is the only term you need to worry about. And that term is just a function of the y operators, right? So this term certainly leaves it. In fact, any Macdonald polynomial it will just act as a scalar on it. So of course this acts, this leaves this space invariant definitely. So clearly this space is also invariant under all the C operators. And therefore it implies it's invariant under the Tx. Okay, so this is therefore the following. Of course, if you write out the action of Ti in the basis of the Macdonald polynomials, then it won't be as simple as the tau I. You will sort of get one additional term. So if you just unwind what we just said, you ask, okay, how does a Ti act on E gamma? The tau I would have just multiplied it, given you some multiple of ESI gamma. But the Ti will also give you an additional term, which is some multiple of E gamma itself. Okay, that comes from the C function. So Ti will map E gamma to some element in the span of E gamma and ESI gamma. So that's what Ti. Sorry, these arrows they don't probably. So what I mean is Ti E gamma is in the C span of E gamma and ESI gamma. Okay, but the point now, therefore, is that these Cx lambdas that we define, they are invariant under the action of all the t's, and of course under the action of the y's. Okay, so this is invariant the t's and the y's. Therefore, it's invariant under the affine Hecke algebra, the algebra generated by these guys. Okay, and this is one of the questions Arvind asked, I think, in my earlier lecture, which is that, so how was Cx defined in the first place? If you recall, your starting point was exactly this affine Hecke algebra. What one did was to induce the trivial representation of the affine Hecke algebra. So we sort of said, okay, let's take the one-dimensional, what we call the trivial representation of the affine Hecke algebra. Then you induce it up to the Daha. So H here is the double affine Hecke algebra. And now what we are noticing is that there are these subspaces here, which are submodules of this polynomial representation. So in other words, now think of this guy and restrict it back to H affine. So think of it as a module for H affine. And then what we are doing is saying, well, here are some submodules that are. So here are some obvious submodules. So Cx decomposes in this manner, where the Cx lambdas are, in fact, submodules for the H affine action. So this is an H affine submodule. Okay, so these are the invariant subspaces. Okay, any questions on any of this?
So just to clarify, lambda is a partition, but the values inside.
Yes, it's a element of Zn which is decreasing, quickly decreasing. Yes. Okay, so now let me look at a subspace of the polynomial representation, if you wish, which is CXSN, which is a symmetric Laurent polynomial. So think of it as, so this is all symmetric, well, not symmetric polynomials, maybe symmetric Laurent polynomials is the right way to say it. So it's all linear combinations of monomials d mu x mu such that these coefficients are invariant under the action of Sn. Okay, for all mu's. So these are the symmetric polynomials. So I'll just call them.
I have a question, sir.
Yes.
So if I add a value to all the lambdas,
Yeah.
lambda 1, lambda 2, lambda,
yes,
and take the resulting lambda.
Take the resulting lambda.
That's called lambda and lambda prime. That is lambda prime is lambda plus k. So some where you add some.
So lambda prime is lambda plus k times 1, 1, 1.
K times 1. Yeah, that's what.
Okay.
Then what is there a relation between these modules?
Between the modules themselves. I don't know, Arun.
Yes, there is. Cx lambda prime will be x1, will be the product x1, x2 up to xn to the k times Cx lambda.
Cx lambda means, I see.
C bracket x lambda dash, C lambda prime is equal to
Cx lambda times, you're saying just the monomial.
Yeah.
Power k.
Exactly. Yeah.
I see. Okay.
Thank you.
Okay. So, sorry, what was I saying? So these are the symmetric Laurent polynomials, you wish. And so here's the first. So I'm thinking of this as a subspace of the polynomial representation. So here's the first observation that, so recall, I mean, this is an action of, the polynomial representation is a representation of the Daha itself, in particular, the finite Hecke algebra. Okay. So the proposition here is that the set of symmetric polynomials, Sn invariant polynomials, can be characterized in terms of the action of the Hecke algebra as follows. So you can think of it as it's those elements of the polynomial representation on which Ti minus t to the half acts trivial. Okay, for all I. Well, this is for the finite Hecke algebra. So I mean for all I 1, 2, 3 till n minus 1. In other words, it's the intersection of the kernels of these operators, Ti minus t to the halves. Okay, so we are just sort of characterizing it in terms of the action of the finite Hecke algebra itself. And the proof itself is easy because we've sort of seen the explicit action formula for the action of the TIs on a polynomial. So let me recall this formula from before. It gives you t to the half f minus t to the minus half txi minus xi plus 1 over xi minus xi plus 1 times f minus SIF. Okay, SIF just means you permute the variables in f, and therefore observe that Ti equals t to the half, just means that the second term is 0. And the only way that term can be 0 is if this guy is 0. So this is 0 is equivalent to saying that Ti f equals t to the half. Okay, in fact, this is slightly stronger. This is in fact also something about for a given I. I don't need to say for all I, but anyway. So the point now is because we sort of know the explicit action of Ti on the polynomial representation, those polynomials which are fixed by Si are exactly the ones on which Ti acts as t power half. And recall now, sort of a useful thing later on. You can therefore also characterize it as those guys on which tau I acts as C minus alpha I check. So tau I minus C minus alpha I check, recall, is the same as Ti minus T power half, right? So here's another, if and only if, maybe I should say. F is symmetric if and only if this operator kills it. So here's just a rephrasing of this in terms of taus instead of t's. Okay. Okay. Let's now look at this bosonic symmetrizer business that we talked about briefly before. So what is it that we want to do? We want to, okay, let me come back to that. So let me first just define this. Okay, so this is, what is this? An element of the finite Hecke algebra we defined before. So let's call it one naught, which is some power of t outside, so normalization, times the sum over the finite Hecke algebra t to the length of sigma by 2 times t sigma. Okay, so this is now an element of the finite Hecke algebra. So recall, the finite Hecke algebra is just the, if you wish, the subalgebra of the Daha generated by T1, T2, Tn minus 1.
Sorry, sigma is in Sn.
Sigma, oh, sorry, yes. The finite by 2, yes. Okay, and so the properties again briefly mentioned before, which is firstly that Ti on this element is exactly t power half times this element, and it's also this element times Pi. Okay, it commutes with Pi for all I. So it's actually a central element, if you wish, of the finite Hecke algebra. And it's all, well, up to a normalization, it's also an idempotent. So it's almost a central idempotent. So one naught squared is, I guess there is probably some power of t somewhere. So, but this is just, so what does this give you? This gives you the Poincare polynomial of Sn. So the Poincare polynomial, recall, is just the length generating function. Just it's t to the length of sigma. Okay, sigma belongs to Sn times 1. And the point here, so I think there's probably also some t power minus length. So the thing here is, I mean, we have t power halves in all other formulas, but this t is actually a t. Okay, so this is just the usual length generating function, not the length generating function of t power half in it.
W naught is the longest element?
W naught is the longest element. Yes. W naught is the longest element of Sn. Yeah, thank you.
So that's just n factorial.
The what?
Version of the n factorial.
Say that again.
That's just the ti the t version of the n factorial. This length generating function, right?
Yes. Correct. Yeah, absolutely. Indeed. Yeah, I mean, in the case of Sn, one knows, yeah, exactly what you just said. So it's 1 into 1 plus t into 1 plus t squared and so on. So this is the explicit length generating function for Sn, 1 plus t squared till t to the n minus 1. Exactly, yes. It's the t version of n factor. Okay, I mean, the proofs of these are not too difficult. Let me just briefly sketch how one would prove this. So if you wanted to prove that Ti acting on 1 naught gives you this multiple of 1 naught. So what is, I mean, we just plug in the definition and, okay, I mean, modulo the Okay, I'll come back to that. So there are these powers of T outside, but let's just look at how would T act on a given T sigma. Right? So 1/0 is essentially a linear combination of the T sigmas. So how does this act? So recall this Hecke algebra thing, which says if the length increases, it's just TSI sigma. But if the length decreases, you sort of get two terms. You get TSI sigma minus T to the minus half minus T to the half T sigma. Okay, so if the length decreases. Okay, so what you have to do is really use this thing. So I will sort of leave this maybe as a tutorial exercise. So all you have to do is now ask, okay, if I take Ti and I multiply it out by this element, how does this expand? You'll have to split it into two pieces. You'll have to look at those sigmas for which SI sigma is length more than sigma, and those sigma for which the length is small. Okay, so split into two pieces and you sort of just work it out. Things cancel nicely and so on. You're only left with T power half times 1. Okay, so just a quick sketch of how the proof goes. And once you have this, the idempotence is more or less trivial. Okay, because that's just saying if you square something, then it's just, you can expand one of them out into its definition, T to the length sigma by 2, T sigma times 0. So by the way, we have shown Ti 10 is T power half 10 implies T sigma 10 is T to the length sigma by 2 10. This is because a given T sigma will just be, you can write it as a product of those many Ti's. Okay, and now you can sort of see why I said this is the actual length generating function with T in it, not T power half. So these two T to the length sigmas by 2 sort of merge together to give you a T to the length sigma. That's really where the length generating function is coming from. Okay, so this is the idempotence of this element. Okay, now so why did we define this bosonic symmetrizer? So I mean, if you sort of recall how this goes in the theory of, say, finite group representations and so on. So when you want to project onto the space of invariants, right, then one uses this projection operator, the idempotent there, the central idempotent. So here again, that the role is played by 10. So yes, the general thing, if I have the finite Hecke algebra acting on some module V, then this idempotent does the following. So look at the idempotent 10. So I keep calling it idempotent. I mean modulo it's up to the normalization. So if you look at the idempotent 10 acting on V, then the point is that the image of this idempotent is exactly the space of invariants. Okay, it's all copies of the trivial representation which are there inside V. It's all those F and V. And recall, trivial representation now means Ti acts as T power half. This is what trivial representation of the finite Hecke algebra means. Okay, so this is what the idempotent does. It's like what we use in, I mean, the finite group representations case, you just take the sum over all G's in Sn. So here you sort of put the appropriate powers of T there. Okay, so again, the proof of this is easy. So if you just see what, so let me just show you how one way of, one direction works. So if you take an element of the image, it looks like this. I apply 10 to some element V of V. The claim is Ti will act on that as T power half. Okay, why is that? Well, we just showed this property that Ti 10 is T power half 10. So I can sort of combine these two together and observe that that's what I get. Okay, and the converse requires the idempotence. You just have to use that 10 square is this one. Okay, so this is some of the key point. This is where the bosonic symmetrizer is coming from, if you wish, because we are now going to pass from what we call the non-symmetric Macdonald polynomial to the symmetric McDonald polynomial. Okay, so how do we construct the symmetric McDonald polynomial? Well, the sort of the place to look is really this. So we take, so we said this, we have Cx, and so let's look at Cx is the polynomial representation, and I'm looking for the space of invariants. And recall, I've already said this, the proposition said that the invariants are exactly the polynomials on which Ti acts as T power half, right? In other words, this is exactly all copies of the trivial representation of the finite Hecke algebra inside Cx. And what I just said just now is that if you want to project onto the trivial representation, what you need is to just act by this symmetrizer 1, 0. Okay? So if we take 1, 0 and I act it on the polynomial representation Cx, what I will get will be exactly Cx Sn. Okay, but we are sort of looking at constructing the symmetric McDonald polynomial indexed by some lambda. Okay, now how do we get that? So the natural place to look is this.
I have one question, exactly one question, exactly. So you're doing this as an abstract, as an infinite dimensional representation, but you could also do this on the level of each finite dimensional representation.
Correct. Yes, exactly. I mean, which is what I'm going to do.
Right.
Cx lambda. So what we are going to do is we're just going to ask, well, let's look at the, let's apply 1, 0 to this. Let's 1 naught. Let's take this idempotent and you apply it to Cx lambda. What you will get is all copies.
Viswanath, I would like a bit of clarification. See, this 1, 0 was the projection to the trivial of the Hecke.
Trivial of the Hecke, yes.
So I would write instead of the Sn there, the Hecke. So what's the relation between the two?
Correct. But that recall was the proposition that I talked. Let's just go on. See, what is the space of invariants is exactly the trivial representation.
Okay. Thanks.
Right? So just another way of thinking about things. So I mean, we want to, so that's in some sense the connection, because see, we say symmetric McDonald polynomial, so we are talking about symmetric polynomials, but we want to rephrase that in terms of the Hecke algebra, right? So that's sort of where we can bring in the Hecke algebra and so on. So that's the connection here. This is exactly the all copies of the trivial representation.
Thank you.
Yeah. Okay. So now, so how are we going to define this? So I mean, the definition more or less suggests itself. You think of it like this. So let's define P lambda as follows. Let lambda be an element of Zn, dominant. So let's define the symmetric McDonald polynomial P lambda as what you get when you apply 1, 0 to the non-symmetric McDonald polynomial E lambda. So I'm going to define it like this, and then there is some normalization factors outside. Okay, so this is P to the lambda by the Concave polynomial of the stabilizer of lambda. So W lambda of T is the following. W lambda is just a stabilizer of lambda. This is all those elements of Sn such that sigma lambda gives you lambda. Okay, and W lambda of T is the same length generating function of this subgroup. So this will be a parabolic subgroup and you take its length generating function. So here's the definition. So this is now the symmetric McDonald polynomial indexed by lambda. So we are going to index it by dominant lambdas. So the point is, so what have we proved so far? What do we immediately know? We know it's symmetric first, because it's obtained by acting 1, 0 on something. Okay, so that gives you a copy of the trivial Hecke, and trivial Hecke is the same as saying it's a symmetric polynomial. So the first, okay, thanks. The immediate thing we observe is that P lambda is, well, firstly, where is it? It's certainly in Cx lambda, right? Cx lambda, recall, we said is already invariant under the action of the affine Hecke algebra, certainly under the finite Hecke algebra. And so when you act 1, 0 on it, 1, 0 is after all an element of the finite Hecke algebra. So it's invariant. It's going to give you some element in the same space. So P lambda lives in this space, and we've also realized, because it's a trivial representation, that it's symmetric. So it's a symmetric polynomial which lives in this space in Cx lambda. Okay, and in fact, I mean, maybe not fact. I mean, we sort of know how to expand it in various ways. So you can, if you want to write P lambda as a linear combination. So observe 1, 0 was the following. So up to this prefactor here, what does P lambda look like? It's T to the length sigma by 2, T sigma. So this was your 1, 0. Okay, acting on E lambda. Okay, and this we sort of already talked about. If you want to figure out how T acts on E lambda, you sort of have to, for example, you could first convert the T's to taus and then figure out how the taus act and so on. So the action can be made more explicit. That's sort of what you want to say. Can be computed explicitly if you wish. As a linear combination. So what I want to say is, finally, this is going to turn out to be some linear combination of the E gammas, where gammas come from S. And maybe we'll say something more about this later. Okay, so the other important point is, so this is now some linear combination of the E gammas. So one thing you lose, one property that the E's had that the P's do not have a priori, is that the E's were actually eigenvectors for the simultaneous action of all the Y's. Okay, but now what we are doing is we are sort of taking linear combinations of these eigenvectors. So this final answer is not, you wouldn't expect it to be an eigenvector for the action of a given Y. Okay, because you will typically get different eigenvalues. We've already said this. These E gammas all give you, I mean, the eigenvalues are all distinct. So it's going to give you something that's not an eigenvector for the action of the Y's, but one nevertheless has an analogous description. So let me just say what that is. You can think of the P lambda. So let's say it like this. P lambda is the simultaneous eigenvector for the action not of Y's themselves, but all Laurent polynomials in the Y's which are invariant under S1. In other words, you take sort of symmetric Laurent polynomials in the Y's. They are now, you can think of them as operators on the polynomial representation. So I'm thinking of all this as action of these on the polynomial representation on Cx. So they give you a collection of operators on the polynomial representation, and these are now simultaneous eigenvectors for the action of these operators. Okay, so let's prove this. We can also compute the eigenvalue explicitly. So what do we need to do? So how do we? So let's take an element in CYSN, then ask, call it f of y. Okay, so we'll try and act it on P lambda. Okay, and what's P lambda? Well, up to that power of T is in front. The prefactor, it's basically you're applying 1, 0 to P lambda. Okay, so let's say some prefactor. So the question is, how does one compute this? So one sort of, we sort of have to understand how the Y's and the 1, 0s interact. So if you can push the Y's past the 1, 0s in some way, then you can sort of try to compute this. Now the point is, these two things actually commute with each other, Fy and 1, 0. Turns out that Fy and 1, 0 actually commute with each other. Okay. In fact, there's more. In fact, if you take a Fy actually commutes with every one of the T's. Fy, I mean this makes use of the symmetry in a crucial way. So if I have a symmetric polynomial, then that commutes actually with every element of the finite Hecke algebra. So this is in particular, it commutes with every element of the finite Hecke algebra. Okay, so let's quickly see why this is the case. Let's use the taus instead of the t's to prove it. So recall, in general, there are often situations where you can happily change the t's to taus, and often the proofs are easier in the taus, and then you sort of see if it works here. So instead of this, let's just look at the taus. So recall this formula. So if I take, how do the y's and the taus commute? That's of course that's the nice commutation relation in some sense. So if I wanted to put fy tau I check, so this is the first thing I would do, which is I try to see how it works on, we shouldn't call it lambda maybe. Okay, leave it as lambda for now. Okay, too many lambdas, gamma. If I take a y and a tau, how does it commute? Well, the tau goes past and the y becomes si gamma. Right? This is the nice commutation relation you have. Okay, this I is really only the finite i's here. So what this means is when the tau goes past the y, it changes gamma to si gamma. And so if I, instead of y gamma check, I had a symmetric function in the, in y. In other words, if I had, say, y gamma check plus y si gamma check, then it commutes. Right? So now, extending this, if I take a symmetric function in the y's, then it will commute with all the tau checks, not just the fixed I. So this logic therefore shows the following, that if I take an fy which is symmetric, then it certainly commutes with the tau check. For all f in cy Sn. And now let's change the tau back to a t. What does that imply? Tau, recall, is just, this was our formula, it's t minus t to the half plus the c's. Okay, but well, these extra terms, these error terms, they all already commute with the y's. They are all just some operator in the y's. They certainly commute with any operator in the y's, right? So this additional term which you incur, this already commutes with fy. So there's nothing further to do. Hence proved. Okay. So what this says is that the finite Hecke algebra, every element of the finite Hecke algebra commutes with cy Sn, and as a corollary, the idempotent 1,0 also commutes. So fy 1,0 is also, it certainly commutes. Okay, so now we are ready to show that P lambda is an eigenvector for the action of fy. So if I compute fy on P lambda, so which as I said, is up to the prefactor, it's just 10 E lambda. So we'll commute these two guys past each other. So I get 10 fy E lambda. Okay, now fy, of course, is E lambda is an eigenvector for the action of the f's, for the for the action of fy, because it's a polynomial in y, and we know how to write the eigenvalues. Right? So recall a given eigenvalue. So let's recall this again. How does a given gamma check act on E lambda? This will just give you some power of q, some power of t. Power of q is just gamma check on lambda. Power of t is you first look at v lambda inverse rho gamma check. Okay, so this is the power of q's and t's, and this is what we call the evaluation in this case. So this is the evaluation map, as we call it. So it's evaluation v lambda inverse rho minus gamma minus lambda of y to the gamma. Okay, so this is eigenvalue on a given term of the form y to the something. And the evaluation just says, you just by linearity, you apply it to every term in fy. So this guy is just some, it's a linear combination of monomials in Q's and T's. It's a complex number, really. So its evaluation, V lambda inverse rho, is a K somewhere. K. The K, remember, is placeholder for T. So this is K times V lambda inverse rho minus lambda evaluated on Fy. The evaluation on Fy times 10 E lambda. Okay, and that's the end of the proof, because 10 E lambda is again P lambda after the constant. So this is the eigenvalue. So when these Fy's act on P lambda, the eigenvalue you get is exactly that guy there. And the point also, I mean, we can simplify it a little bit more. Observe, V sub lambda was the element which sorted lambda in ascending order. That was supposed to be the definition, right? So this, so in some sense, you can think of this as W naught. When you say that, I'm starting to worry. It's supposed to be the minimal length element which sorts it. Okay, I'm slightly confused. So is it? It's maybe not W naught, but rather the longest element in W mod W lambda in some sense. Maybe. Is that all right, Arul? Okay. Okay. So I mean, if lambda is at least, you know, if it's regular, if all the lambdas are okay. Actually, it doesn't matter because actually it doesn't matter because you're going to evaluate it on lambda finally. Okay, sorry, I'm slightly confused, but let me just say, at least if lambda is regular, meaning if lambda 1 greater than lambda 2 greater than lambda 3 and so on, then this V lambda is just the element which sorts it in ascending order is just W naught, the longest element. Okay. So if you put that in here, W naught inverse is W naught, and W naught on rho is just minus rho. Okay. So this evaluation really in this case is actually minus K rho minus lambda. So that's what you're doing. It's evaluation at this guy. So this is finally the eigenvalues are following. It's evaluation at minus K rho minus lambda of this polynomial. So this is the eigenvalue. Okay, so that's so we have shown that so to quickly summarize, we have shown that the P lambdas are all symmetric functions. They lie in Cx lambda. In other words, they are linear combinations of the non-symmetric Macdonalds in that component, and that they are eigenfunctions for the actions of the symmetric polynomials in the box for those operators. Okay, so
sorry, can I ask? I'm
yes.
a bit confused what role K is playing.
Yes, K is, I mean, think of it as sort of a lazy placeholder for T. So we don't want to keep writing, see, T power K is Q.
Oh.
It's just, you know, you're replacing T with another unknown.
Yeah, sure, thanks.
Yeah, so you just, I mean, slightly more compact notation. Okay.
This written with the point of view of eventually going to Jack polynomials. I mean, this is the kind of thing one does.
Q power is some power of Q, right? For the Jack.
Are you going the other way? Is it T power K is Q or Q power K is Q?
Oh, sorry. T is Q power. Yes, thank you. Correct.
Yeah, and then if you take Q to 1, then you get
yes,
Jack polynomial.
Absolutely. Yes, indeed.
Okay.
Okay, so
one other question. Do we know about the dimension of the fixed point space, the invariant subcomponent of Cx lambda is?
Absolutely, that's exactly what I'm saying.
Okay.
So the point, therefore, so the natural question, as Apurva pointed out, is the following. So we just symmetrize starting with E lambda, right? So we took Cx lambda, we sort of symmetrized only one particular guy in that, which is the E lambda itself. Right? We only took the E lambda and you symmetrized it, and what you got is the P lambda. But then the natural question is, what is the dimension of this fixed point space, the trivial representation? In other words, what if you pick some other E gamma in the same space and you symmetrize that? What do you expect to get? Okay. And it turns out the answer is, well, you don't get anything new. You get some multiple of P lambda. You get the same thing up to a constant. Okay. So I'll just call this F gamma using Arun's notation. So this is called the symmetrization of E gamma. Symmetrization. Okay. And so here's the statement. Has a sort of the explicit constant also can be worked out. So what is F sub gamma? Recall, you just apply 1, 0 to E gamma. Okay, and P lambda, rather, let's say without the constants in front, what you call the symmetrization, F lambda, which is 1, 0 on E lambda. So the question is, how do these two things relate? So recall, this is like P lambda, except for a constant. So if you symmetrize E gamma versus you symmetrize E lambda, how are they related to each other? So here's the statement. They sort of differ by an explicit constant that you can write out. So F lambda. So here's the proposition. F lambda is the following multiple of F gamma. It's the product. So there's a nice product here. You take Ij running over the sort of inversions of what? Well, gamma and lambda are related by some wild group element, right? So you can write some Z gamma of gamma. So let's take the minimal length element which maps lambda to gamma. Sorry. Okay, so this is the minimal length permutation which maps lambda to gamma. Now you run over all inversions of that permutation, Z gamma, of 1 minus q to the, so this is lambda, inner product of lambda with the corresponding positive root, so it's lambda I minus lambda j, t to the, this is the inner product of that root with rho, which is j minus I, divided by the same thing with a t in it. So 1 minus with an additional t. So q to the lambda I minus lambda j. The same thing multiplied by a further t times t plus 1. So that's the explicit constant times the F gamma. Okay. And so I'm almost out of time. So let me just briefly say, so these products here should remind you of the C functions. Okay, so if you recall how the C function was defined, it had 1 minus t y to the something divided by 1 minus y to the something. Okay, this is actually the inverse. What you're seeing here is the inverse of the C function. And so let me maybe just show you how this works for maybe one simple case. So if I try to symmetrize, so let's just say I pick a certain lambda, and let's just look at a gamma, which is just one step away. So you take, suppose lambda is a dominant guy, and with an inversion on the ith place. And let's call gamma to be just SI of lambda. So the question is, if you symmetrize gamma, what do you get? Well, you apply 1, 0 to E gamma. Okay, and recall we have done this. How do you get E gamma itself? So we want to compare these two guys, this versus the symmetric multiple polynomial. 1, 0 E lambda.
Sorry, one quick so the corollary is that those invariant subspaces are all one-dimensional. Right?
Yes, invariant subspaces are all one-dimensional.
Thanks.
And spanned by the symmetric multiple.
That's right.
Okay, so how do we get E gamma from the next guy? Well, gamma is just SI lambda, and recall this is the thing I began today's thing with. We had from last time how to get SI lambda from SI lambda from E lambda. You just apply a single tau H. Okay. Now, so here's the point. So forget the t power half here. Just push that out. So I'm now in a situation where I want to push the 1, 0 past the tau H, because I want to finally compare it against that, right? I need to figure out what is 1, 0 E lambda versus 1, 0 tau H E lambda. Okay. And again, so where do the C functions arise? So observe 1, 0 is Well, what property did it have? It is killed by Ti minus T power half. This was exactly, one way of thinking about 10. It's the trivial representation. So this is what 10 is. It's somebody who's killed by Ti minus T power half. And recall, you can change Ti to tau I like this. Ti minus T power half is just tau I minus C alpha I. Okay. So in other words, this 10 tau I check can just be replaced by 10 times the C function. Okay, so this guy, so this is sort of where the C function comes from, the C operator. So this is like there's a T power half outside, there's a C operator times E lambda. But of course, the C operators act nicely on E lambdas because they just give you the corresponding eigenvalue. Okay, so this eigenvalue here is exactly what you're seeing in that product formula. When this particular C operator acts on the non-symmetric Macdonald E lambda, in this particular instance, what you'll find is exactly, recall what the C function was. There's a T to the minus half. There's 1 minus T y to the minus alpha I check. 1 minus y to the minus. Okay, so when this acts on E gamma, you'll sort of get a Q and a T monomial. There's a Q and a T monomial on the bottom. But notice the particular form of this. The thing on top it's the same as the thing on the bottom, except there's an additional T in it. Okay, so that's exactly the form that you're seeing. Okay, and then one sort of just manipulates this eventually to get this. So final moral of the story is that you have the polynomial representation on the one hand, which splits into a direct sum of Cx lambdas, and the symmetrizer, the bosonic symmetrizer or the idempotent of the finite Hecke algebra maps this exactly to the space of invariants. And each of these spaces maps to a one-dimensional space, which is spanned by the corresponding symmetric matter. Okay, great. So let me, I've gotten exactly to the end of what I wanted to say. So let me stop here. Next time I will sort of talk about orthogonality and triangularity. So this is sort of what's left. What I want to say. Yeah.
Any questions or comments?
So I have a quick question. So can you go back to page 15? And
Page 15. You actually noted down the page on which you had.
Yeah, because I didn't want to interrupt the flow.
Yes.
Yeah, so here I'm confused as to why. So earlier, the action of the tau I checks gave you either, did either give you something SI gamma, or it just gave you gamma depending on whether there was an inversion or not. But now, independent of that, you seem to be switching. So, right, when you commute past, so y gamma, when it commutes past tau
No,
I check.
not the y's, not the y's. That was on the Macdonald polynomial, right? See, tau I check acting on E gamma was giving you ESI gamma, or some multiple thereof. Okay? So this is an equation. This is just inside the double Hecke algebra.
Okay.
Double affine Hecke algebra. You are not.
So this is not on the representation. This is just at the level of.
Yeah, it's not on the representation.
Okay. Thanks.
And and also it's on the y's rather than. There are no E gammas in the future.
Right. Yeah, that's what I meant. Yeah, thanks.
Any other questions?
This x1 through xn, this which moves from one lambda to the add the k, as I was asking.
Mm-hmm.
So that commutes with all the, what is the correct thing to say? Is that it commutes with all the affine Hecke algebra elements?
multiplication by this x1, x2, xn operation. Not sure I understand your question. So you're saying on the polynomial representation, look at the operator which multiplies everything by x1, x2, xn.
Yeah.
And you're asking if that commutes. Is that operator something we can realize purely? Is that an affine? Is that a double affine Hecke algebra operation form? I don't know, Arun, is it?
Yes, it is. It's symmetric. It's a symmetric polynomial, so it commutes with the finite Hecke algebra.
Oh, I see. So okay. That's exactly this thing. Okay, except so this is just written for the y's, but the same thing holds if you also. I should have said that actually. So, I mean, maybe by duality, if you wish, you can replace the y's by x's. So if you take a symmetric polynomial in the x's, cxx, and you take any element of the finite Hecke algebra for the same reason, they will sort of come in.
But what about the affine Hecke algebra? So these are modules, CX lambdas are modules for the affine, right?
Yes.
Isn't that correct? When you wrote that restriction is equal to direct sum of.
Yes. CX lambdas are module for the affine Hecke algebra. Correct. So you're saying this operation now.
What about when you
No, you see, this operation involves the x's, right? Somehow. You see, the affine Hecke algebra is the one which is generated by the t's and the y's. That's the affine Hecke algebra you're looking at. Whereas this operation you're proposing involves the x's.
I understand. So when I move from one module to the other, so the question is this module? So is CX lambda the isomorphic to CX lambda plus k, as I was asking?
As a module.
As a affine Hecke algebra.
So their isomorphic is finite, but the question is about affine.
I think it is, but there you have to do some more check to show that x1 up to xn commutes with the element g.
Okay.
Yeah.
So the relation between, in the double affine Hecke algebra, the relations between the x's and the y's are not particularly nice to write out in general. Do they have a nice relation? X mu, y gamma, for example.
No, only the top term is easy. Okay. Because the top term you can compute by thinking of it as if it were in the double affine Weil group, and then it's a Heisenberg, and it commutes with the power of q. But the lower terms are quite a mess, I think. I don't know how to control them.
I don't think I followed what you said, Arun. Could you be a little more explicit? When you said the top term, what did you mean?
So x, suppose I want to take a product of x to the mu, y to the lambda check equals, and then I would like to write the y's on the left. So y to the lambda check, x to the mu, but there are more
plus
terms.
Dot. Okay, plus dot.
Okay. And the dot, I don't know how to calculate.
Yeah, thanks.
Okay, let's thank Viswanath. If there are no questions.